Hello, everyone. Sorry for the lag. I'm not your session chair. He's probably enjoying his lunch. But I'm one of the program chairs, so stepping in. It's a pleasure to introduce SIGCOMM'25 from Tencent, who's going to talk about Fornax, which is a hardware-centric session management system for large public cloud networks.
Okay, hello everyone. I'm SIGCOMM'25 from Tencent. Today I'm going to share our network about Fornax, a hardware-centric session management in large public cloud network. Nowadays, cloud networks are usually support various network functions such as virtual network, NAT, and firewall. Those functions can be abstracted into a match action processing paradigm, and which is implemented by generating entries in the virtual switch. And currently, cloud provider usually leverages hardware such as SmartNIC to accelerate cloud network. And this figure shows that a typical workflow of hardware acceleration for cloud hosts. The first packet will be redirected to the software, which generates corresponding forwarding information, and the software can offload the forwarding information to hardware as a flow entry. And finally, the subsequent packet from the same flow will be directly forwarded by the hardware. Meanwhile, the software needs to manage the flow tables offloaded to the hardware. When flow entry is invalid, the software needs to age it timely. And then when the network policy changes, the software needs to detect it and update the flow entries. And when the memory experiences errors, the software also needs to detect it and recover the flow entries. This figure shows a traditional hardware table management mechanism, which we call the software-centric management architecture. Because it relies on the software to periodically scan to manage the hardware flow table. However, according to our measurement in large-scale Cloud 1, we know that the flows emerges new features. Firstly, the size of flow can become extremely large. This figure shows that shows that those hosts on enormous flow tables, which can be far exceed 1 million. Surprisingly, we can say that for host E, the flow table even reached 60 million during a certain period. To handle above features, a conventional acceleration strategy is to offload the hot flow entries, and while most of flows still necessitates forwarding all packets to the software. This approach only needs to manage a few offloaded entries and can thus exhibit good scalability. However, its acceleration capability heavily relies on the traffic patterns. However, we show that the distribution of flow can be fairly uniform. This figure shows the traffic distribution collected from our production. It can be observed that those hosts exhibit various distribution features, with some exhibit fairly uniform traffic distribution, such as host C and host D. For example, the top 10% of flows in host D only carry 28% traffic. So a more attractive acceleration strategy is to offload all flow entries. while the software only needs to take responsibility of managing those offloaded entries. Since this approach needs to periodically scan the status of all offloaded entries, its management overhead heavily relies on the table size and the scanning frequency. Unfortunately, the variation of flow entry can be significantly substantial and require frequent scanning. Here, variation is calculated by the new flow entries created in this minute relative to the flow entries in the last minute. It can be observed that those hosts experience high-frequency entry variation and can vary most entries within a minute. For example, host B can even reach more than 100% variation ratio at a certain moment. Therefore, as a large public cloud provider, we must be able to address the worst case. However, the results of the management plane are extremely limited and can be heavily overloaded. First, it can occupy excessive storage resources due to the full backup of the flow table. Second, it can burn CPU resource due to the frequent scanning of the extremely large flow tables. According to our analysis, the fundamental shortcoming of existing work is the flow abstraction. Currently, the flow entry only contains forwarding information for packets and doesn't save any states for entry lifecycle. Therefore, it can only rely on the software to fetch back bidirectional entries and detect changing in entry lifecycle with more information. To address the above problem, we advocate for radical new mechanism to shift the management paradigm from the software-centric architecture to the hardware-centric architecture. As shown in the figure, we first adopt session as the basic management unit rather than flow. Then we design a two-way protocol to facilitate the management process. However, we encounter three challenges in the design of the hardware, software, and the interaction between them. Firstly, the hardware should be powerful enough in function but simple enough in implementation. However, the two requirements inherently present a contradiction, as a simple implementation may struggle to provide power functions. Second, the software should be able to accommodate extremely large flow tables with little storage overhead. However, common approach like reducing storage content and optimizing storage structure can either impact the management function or yield limited benefits. Third, the interaction protocol should efficiently complete the management workflow without losing high performance of hardware and scalability of software. Since the hardware and software are inherently different, we should carefully allocate the management responsibility between them. So we present our Fornax, which consists of three aspects: session-empowered hardware engine, lightweight software manager, and a hardware-driven management protocol. To achieve the powerful but simple management function in hardware design, we propose only providing the minimal yet essential set of atomic functions for simplicity. Then the upper-level application can assemble atomic functions to complete complex management. Specifically, the hardware contains two parts. First, we adopt session as the basic units, and the session entry aggregates bidirectional flow entries and can maintain the connection status. Besides, session entry augments relevant in-context states and can boost the management of entry lifecycle. Second, we introduce the hardware session engine to enable two-way interaction. The engine defines the format of events and can automatically notify relevant hardware events to software. And besides, the engine offers various operation interfaces and can support locally operation of session entry of the software. To accommodate extremely large tables with little storage overhead, our key insight is that the management information is only used in rare circumstances, making it unnecessary to maintain complete content constantly. Therefore, we propose dispersing the information across multiple locations and only retaining volatile states. When required, the information from multiple locations can be combined to restore the complete content. As shown in the figure, the management information can be categorized into 3 types, and the square brackets indicates redundant information that can be eliminated. The first type is the flow entry. Since their action can be regenerated in the slow path, we can treat the computation for storage and regenerate those actions when required. The second type is the runtime information. Since most packets are directly handled in the hardware rather than the software, we can put all statistics and partial stats onto the hardware. The last type is the metadata, which is utilized to maintain the table structure. With the substantial reduction in entry content, we can optimize the table structure, and most metadata is no longer required. To efficiently complete the management workflow without affecting the hardware software, our key insight is that hardware is closer to the session entries with timely detection, and software can gather more information and offer greater flexibility. Therefore, we propose a management mechanism where hardware takes the initiative to trigger events and the software responds to various scenarios passively. As shown in the figure, we have 3 management protocols, including aging protocol, changing detection protocol, and error tolerance protocol. All those protocols follow a similar workflow. After the packet arrives, if the hardware detects a management requirement for this session, such as the entry is outdated, it actively notifies a management event, so the software can take appropriate management operation, such as updating the entry in the hardware. Finally, we have implemented Fornax on a smart NIC and run it on millions of servers for 2 years, serving network traffic from billions of users on Tencent Cloud. To demonstrate the advantage on the management workflow, we compare it with the existing work, such as Tiara, XLNet, and OVS. Those figures show the comparison of the CPU usage over time in agent and change detection scenario and error tolerance scenario. And we can see in the figures that we normalize the size of the session table to 1 times, 2 times, and 4 times. We can observe that with the increase of the table size, the CPU usage of the current solution can increase quickly and even suffer from the data plan crash. However, Fornax can effectively reduce the software CPU usage by 17%. This is because the Fornax relies on the hardware trigger for entry management rather than frequent table scanning of the software. We then evaluate Fornax with 3 sets of actual traffic and compare its CPU usage and packet latencies with existing solutions. Those 3 figures represent most typical application from the small-scale application and the large-scale application. It can be observed that with the increase of the application scale, the CPU of current solution can suffer from overload, resulting in rapid deterioration in packet latency. However, Fornax exhibits only a moderate increase in CPU usage, and while maintaining minimal impact on the packet latency. Those findings indicate that Fornax can effectively reduce the resource overhead. We also collect the resource statistics in production. This figure shows a heat map depicting the distribution of the table size and CPU usage among about 12,000 random hosts. It can be observed that the table size is predominantly concentrated around 100,000, with a few hosts reaching an exceptionally large size of 16 million. Meanwhile, the CPU usage primarily clustered around 20%, with the highest usage not exceeding 64%. The finding indicates that our approach is capable of satisfying the management demands of millions of servers in our data center. Finally, we present the 5 important contributions we made in Fornax. Firstly, Fornax proposed a radical new mechanism to shift the management paradigm from software-centric to the hardware-centric. Fornax is the first of its kind system that adopts session as a management unit. Fornax has been deployed on millions of servers for 2 years, and the testbed results and production results show the performance gain of the Fornax. That's all. Thank you.
My name is James Zheng. I'm a session chair today. Sorry for being late. Do you have any questions for Cong Cong? Can you pass the mic? Yeah, on the back.
Hi, I see you mentioned there's a session abstraction and there is the main component. Is bidirectional flow entries, and it has some relevant in-context state. May I ask, can you explain more about the in-context state in depth and how they are actually being used? Thank you.
Okay, that's a great question. The TCP state machine mechanism for aging protocol and entry version for change detection protocol, such as the CRC to maybe the memory errors, and so this it's about this all. Thank you.
Okay.
Thank you. Thank you for the great talk.
Hey, Kong Kong.
Hi.
I was wondering if you compared with other smart NICs, like the ones from AMD Pensando, that don't quite have your abstraction, but have other abstractions that let them implement stateful firewalls?
You mean that we have implemented for the other network functions? Or?
The key, which was your session-based abstraction and implementation, the contrast would be an alternate implementation. Say by using some hardware vendors' abstractions to implement a stateful firewall. So I was wondering if you tried anything like that, say with AMD Pensando. AMD Pensando has a stateful firewall in there.
So I think the question is that, is there any, let's say, commercial products or some other NICs? Have you evaluated that kind of NICs instead of writing your own session manager?
Okay, so this is a good question because maybe some work has not been open sourced, so we only use a prototype or just use the mechanism from the paper to for the comparison. Yeah.
Okay. For the time, let's thank Song Song again. Thank you.